All right, let's take a look at question 10 here on page 603. So, using the measured speed and the rest mass of an electron in a television picture tube has a classical kinetic energy of 30 kilo electron volts. Determine the actual kinetic energy of the electron, so accounting for relativistic energy as well as the rest energy. Okay. So first things first, let's figure out what the speed of the electron. So the first part of this question, we're essentially assuming everything is classical, which means that the kinetic energy of the electron would be given by half times mass of the electron times the speed squared. Okay. And so because we're using the rest mass of the electron, we're not worrying about any relativistic effects here. Okay. The only thing that we have to do is convert the given kinetic energy, which is 30 kilo electron volts. So that's 30 times 10 to the 3 electron volts. Let's first convert that to joules, right? So the conversion factor between electron volts and joules is essentially just the charge of so it's 1 electron volt equals 1.60 times 10 to the negative 19 joules. And so what we can do is we can use this conversion factor to rewrite this energy in joules instead. So we have 30 times 10 to the 3 electron volts. Then we're going to multiply by 1.60 times 10 to the negative 19 joules per 1 electron volt. All right, and when we do that, let's see what we get. So 30 times 10 to the 3 times 1.60 times 10 to the negative 19, we get 4.8 times 10 to the negative 15 joules. Okay, so we have our classical kinetic energy now. So now what we can do is use that to figure out what speed it's traveling at. So the kinetic energy is equal to half mv squared. So I can rearrange this for the speed. So I get the v squared is equal to 2 times the kinetic energy over the mass. And I'm just going to square root both sides here. So the speed is given by the square root of 2 times the kinetic energy over the mass. So let's see what the speed that this electron is traveling at. So I have 2 times 4.8 times 10 to the negative 15 joules divided by the mass of the electron. So 9.11 times 10 to the negative 31 kilograms raised to the power of a half, so the square root. Let's see what we get here. So 2 times 4.8 to the power of negative 15 over 9.11 to the power of negative 31 square rooted. We get a speed of 102,654,130.3 meters per second. So the electron is moving pretty quickly here. Okay. Now that we have the speed that it's moving at, what we can do is determine the actual kinetic energy of the electron by using the relativistic energy as well as the rest energy. Okay, so to do that, what we can do is we can use the following formula. So we have the total energy contained within the electron is equal to the rest energy plus the kinetic energy. Okay, and so the total relativistic energy is given by mc squared times the Lorentz factor, so over 1 minus v squared over c squared, square rooted. The rest energy, that's just E is equal to mc squared. Okay, and so using this, we can figure out the relativistic kinetic energy, right? That's the thing that we're looking for there. So what we can do is we can rearrange this equation here. So we get Ek would be equal to E total minus E rest. So E total, that's mc squared over square root of 1 minus v squared over c squared minus our rest energy. Okay, so now we can plug in all the quantities that we have here. So the mass of the electron, the speed that we're moving at is what we found in the previous part there. So let's plug into this formula and we'll see what we get. So give me a second here. Minus so when I do that, I get a kinetic energy of 5.267715171, and of course that's measured in joules. And so now I want to see what this is measured in electron volts. So I want to convert this to electron volts. So to do that, I just divide by 1.60 times 10 to the negative 19, and we get a value of 32,923.21982 electron volts. So that's going to be approximately 33 kilo electron volts. Okay. So comparing this, the relativistic kinetic energy, what we notice is that it's very slightly higher than the classical kinetic energy, right? So we had 30 kilo electron volts was the classical, or the kinetic energy that we had in the classical case, and then the relativistic kinetic energy is 33 kilo electron volts. All right. So I'll pause there, I'll cut this off, and then I'll do question 12 in a second.